Video 2 of Chapter 10. We are now going to step up our number of samples to a 2-sample t-confidence interval for the difference in means. Now the question we're going to explore in Video 2 is, do plastic bags from Target or plastic bags from Walmart hold more weight? A group of AP Stats students decide to investigate by filling a random sample of 5 bags from each store with common grocery items until the bags ripped. Then they weighed in grams the contents of items in each bag to determine its capacity. A 95% confidence interval will be calculated. Now, if I take a look at just my raw data here, I'm noticing that it appears to be that the Target bags are holding more weight than the Walmart bags, right? I mean, there's only one Walmart bag that reached over 10,000 grams in capacity versus all the Target bags were over 10,000. So looking at these small sample sizes here, I get the feeling that Target is probably going to be better, but is it statistically better than Walmart's bags? So let's find out. So we're going to follow our 3 C's like we've been doing. We're going to check our conditions, we're going to do our calculations, and then we're going to write our conclusion. So first with conditions, we're going to check the random condition, the independent condition, and the normal condition. So for the random condition, again, you have to be told about random samples, SRSs, or random assignment of treatments. So this is the same as it was for one sample, except now we have to have 2 of each of these things. Now there could be times where they say you have one random sample and you have an SRS of another, as long as they're getting at that you really have 2 random samples of some kind, then you're okay. Now, the problem stated a random sample of 5 bags from each store. So we do have a random sample of bags from Target, and we do have a random sample of bags from Walmart. Now, the independent condition, we are sampling from a population of bags from each store, so we do have to check the independent condition here. This wasn't like we had a group of volunteer bags that said like, oh, use me, I'll do this for science, for statistics. So we do have to check, is the population at least 10 times the sample size? So the first population, I might say, are all plastic bags from Target. And are there more than 50 plastic bags? Because 10 times my sample size of 5 would give me 50. Are there at least 50 plastic bags from Target? And that is definitely a true statement. I don't even need to think we need to say assume true. Like, there's definitely more than 50 bags from Target. Same thing goes for Walmart. Are there at least 50 plastic bags from Walmart? And again, this isn't something I would say, I'm going to assume it's true. Like, I definitely know that that's true. So the independent condition, we are good with. Now it's that normal condition. So remember, there are 3 things to consider, and I would do these in order. So number 1, if both population distributions are approximately normal, then we would write both population distributions are normal, so the sampling distributions are normal. Or we could say the sampling distribution is normal because both population distributions are normal. So as long as you state this in either order, it doesn't really matter. The thing to note is that we are talking about 2 population distributions, right? The distribution of bags from Target and the distribution of bags from Walmart. But in the end, we are only going to have 1 sampling distribution. And it's really going to represent the sampling distribution of the differences in the means. So don't tell me that there are 2 sampling distributions unless you want to tell me that the differences of the 2 sampling distributions leads to a sampling distribution of differences that are approximately normal. Then I guess technically you could state it that way. Now, the second way that we can try to do this is if we have big enough sample sizes for the central limit theorem to apply. But we were told that we only had random samples of size 5. So this doesn't work out here. But if it did work out, we would write the sampling distribution is approximately normal due to or because of the CLT with 2 large sample sizes. Now, one other thing I'll mention before we get to the third one is, what if they told you one population was normal and the other population was, let's say, skewed, but that skewed population distribution, they used a big enough sample size for the central limit theorem? Could you write it in such a way that you're using kind of like the first part for the one distribution, and then using this second part to discuss the central limit theorem for the other distribution. And yes, it is possible that there could be some sort of mixing and matching in, okay? But ultimately, it's probably going to come down to option number 3, where if they don't tell you anything about the population, and if you don't have a big enough sample size, which is the case here, then we're going to need not just one graph, one box plot, but we're going to need 2 box plots of our data. Now, we need to be on the lookout, again, for strong skewness and or outliers. Now, I wrote out really what we're going to have to do to get those box plots on our calculator. So you're obviously going to need to put the data into 2 lists. You need list 1, let's say, is Target data, list 2, Walmart data, and then you're going to go to stat plot. So you're going to have to press second y equals on your calculator. Then you're going to have to go to, say, plot 1, make sure it's turned on, select the box plot that shows outliers on the ends, and then tell it you want to make a box plot of, let's say, the Target data, list 1. Then you're going to have to go back out to plot number 2 and turn it on. We hardly ever looked at 2 graphs at the same time, but we really want to take a look at these 2. Now, you could do it one at a time and then show it, but when you show both of them at the same time, it really does kind of show you if there's really going to be a difference between these 2 distributions. So plot 2, again, select the box plot that shows outliers, select your Walmart data. And then you can press graph, and then you're probably going to have to hit zoom 9, and then it'll fit it onto your screen. So I just wanted to show you what those 2 box plots look like here. So this is of our Walmart data, and this is of our Target data. And you can see the Target data clearly is ahead of the Walmart data, where it appears to be that there will be a significant difference between these 2, right? That there will be an ultimate difference between the qualities of these 2 bags and how much they can hold. But we're going to have to, again, kind of prove that's true mathematically. But this gives me a good idea. We're probably going to see that happen. So when we have those 2 box plots, we can clearly look at these and say there are definitely no outliers. I wouldn't say there's any strong skewness. There's definitely some skewness, but not that I would call, disproportionately strong. So I would state the sampling distribution is approximately normal because the data sets, or the box plots, plural, show no strong skewness or outliers. And again, we need to show evidence, graphical, pictorial, visual evidence of what those box plots look like. And so you just copy them down to the best ability of your ability on your paper. Now again, I know I say here the sampling distribution, and remember the sampling distribution is the sampling distribution of the differences. We're really kind of first stating that these individual box plots are going to produce sampling distributions that are approximately normal, but in the end we are going to subtract those 2 or normal distributions to get a sampling distribution of the differences that is approximately normal. Now, on to our second C, our calculations. This is the lovely formula that if you want to use formulas, you could use the formula here. And on our generic formula, again, we are told statistic plus or minus critical value times the standard error of the statistic. The standard error of the statistic is this lovely formula, which you will be given on the formula sheet. But you will be in charge of knowing for the statistic part that it's really going to be the difference of the sample means. And where are those sample means going to come? No, wait, I don't have sample means. I don't have sample standard deviations. I didn't have those numbers. Where do I get those numbers from? Right? I was just given the 5 data points of the Target bags and the 5 data points of the Walmart bags. So what we're going to need to do, and thankfully, since we've already made the box plots, we already have our data in 2 lists. So again, I have my Target data in list 1, my Walmart data in list 2, and what I'm going to need to do is go back and use good old 1 variable stats. And I'm going to do this separately. I'm going to do it for the Target data, and then I'm going to go back and redo it for the Walmart data. And some of you might be wondering, hey, right below 1 variable stats is a 2 variable stats. Could I use two variable stats with list 1 and list 2, and it does the one variable stats, instead of doing it twice, it's only going to do it one time? And I would say yes and no. You can use two variable stats as long as you have equal sample sizes. So technically, with our 5 bags each, I could technically use two variable stats. And so it's going to give me data all about my X's, and then it's going to tell me about data or statistics that are listed in terms of Y. I would just do one variable stats twice. Again, if you had two unequal sample sizes and you try using two variable stats, then it's going to give you an error of some kind. So one variable stats with my target data, here is my sample mean, and then SX, here is my sample standard deviation. Do not use this sigma X. That is just an estimate of the population standard deviation, which is not entirely known to be true. So we're going to use our sample standard deviation. And then, of course, we're going to use our sample size of 5. Then do one variable stats for our Walmart data. So here's the sample mean of the Walmart bags. Here's the sample standard deviation for our Walmart bags. And again, we have 5 bags to use there. So now we've got the sample mean, the sample standard deviation, and our sample size, but we still got to get that t critical value. So how do we get a t critical value when there's 2 samples involved, right? Because t distributions needed a sample size in order to get degrees of freedom, but what happens when there's 2 sample sizes? We're still going to get to use inverse t, and there's 2 options. There's a very complicated way and a approximate way of getting degrees of freedom here. The first way is the very complicated Satterwati formula. And if you want, you could absolutely use this crazy formula here to get your degrees of freedom. I have never once in my entire time teaching AP Stats used this formula specifically. One year I had a student that was like, you know what? I'm going to use this formula. And he memorized this formula and he actually used it correctly in a problem. And bravo for you. But you don't have to use this formula. Our calculator is going to use this formula and it'll tell us what the answer is, but we don't have to worry about this craziness here. Now, the other way is what's called the conservative approach, and it's going to use degrees of freedom using the smaller sample size, -1. Now, since we had equal sample sizes of 5, then there's a tie, so we would just take 5 minus 1, and so we're going to end up using 4 degrees of freedom whenever we use inverse t with our calculator. But again, it's whatever one is the smaller sample size, -1. So, what's our t critical value for 95% confidence with 4 degrees of freedom? Well, if we got 95% confidence, one tail area is going to be 2.5% with 4 degrees of freedom, and then we can hit paste and hit enter. If we had an older calculator, we would have to go 0.025 comma 4 end parenthesis, and then we could hit enter from there. And that is going to give us, let me cheat here and look ahead, 2.776 is going to be that t critical value that we'd get. Now, keep in mind the calculator is going to say negative 2.776, but we just drop the negative. So if I wanted to use that grand formula, I could plug in all of those numbers now. And oh my goodness, if you make one little mistake typing all this into your calculator, you're going to screw up. But this is the confidence interval that you should get if you've done everything correctly. So from 594 to 6589 grams is the 95% confidence interval for the difference in the weight that the 2 bags can hold. There we go. Now, what if I just wanted to use my calculator to do the confidence interval instead? Well, then I would have to name the procedure. This is a 2-sample t confidence interval for the difference of means. Or you could say mu1 minus mu2. So for the difference in means, either in words or symbolically mu1 minus mu2. Population mean 1 minus population mean 2. If you go over to your stat button and scroll over to tests, you're going to want option 0 here, a 2-samp T int or interval. Now, if for whatever crazy reason they gave us the 2 population standard deviation sigmas for Target and for Walmart, then we would end up using option 9 for the Z interval. But again, for the most part, we are going to be using the T distributions. So select option 0. You have options of using data or using statistics. Now, we already have our data in lists, so I would just select the data option. Use list 1 and list 2 where we have our 2 lists at, or you would select whatever list you have your data in. Frequency 1, frequency 2, we want to leave these at 1. Leave them at 1. And then sea level, 95%. For pooled, I always want you to leave it on no. And we can talk more in depth about what pooling means. It's really going to be more helpful for our AP Stats exam takers, but by default, it's no. You're always going to leave it at a no. And then from there, you could hit calculate, and it'll give you the confidence interval. Or if you wanted to put in the statistics, or maybe they gave you the statistics in the problem to begin with, and these are those numbers that I got from one variable stats. So I typed all these numbers in from Target. I typed all these numbers in from my Walmart statistics. 95% level, no to pooling, hit calculate. So either of these 2 options leads me to this screen over here. Now, the only thing you need to write down is the confidence interval and the degrees of freedom. But notice the degrees of freedom are some crazy sauce numbers here. Like, how on earth did it get 7.513133718? Oh, it used the crazy Satterwadi formula. So you have to write out, because again, there's 2 different ways to do degrees of freedom. You can either use the crazy formula, or you could use the smaller sample size -1. The calculator doesn't mind using the crazy Satterwadi formula. So you have to write out how many degrees of freedom. Can you round this to say like 7.5 or 7.51? Yes, you don't have to write out all of those decimals in there. But one thing I want to point out to you is the big difference between the confidence interval that we got with the formula, with our 4 degrees of freedom, versus the confidence interval that we just got in the calculator with the more precise degrees of freedom here. So look at the smaller number here, 594 versus 1073. I mean, there's almost a 500 gram difference between the smaller value for our confidence interval, right? And take a look at the upper end. We're at, almost 6,600, and the upper value for the other one was 6,100. Again, almost a 500 gram difference. That kind of seems large, right? Why is there that much of a big difference? And it's all about the degree of freedom differences in here. So earlier when I said that option 2 was the more conservative approach, and we used that smaller sample size -1, I said with this option, the resulting confidence interval has a margin of error as large or larger than is needed for the desired confidence level. So with that 4 degrees of freedom, it's going to make the margin of error bigger, which is going to make our interval even wider than what it needs to be. So it's just like a safe estimate. If you use a smaller number of degrees of freedom, it's going to increase the margin of error, and then it's going to give us more values to consider. So if we want the more exact answer, we really should use the calculator, or if we want to use that crazy Satterwadi formula, that's technically the better way to get the confidence interval. So I just wanted to let you know, you will see a difference. Now on the AP exam, which of these 2 confidence intervals will they give credit to? They'll give credit to both of them because technically they're correct. So you just have to state, remember, what the degrees of freedom are with your confidence interval, because there could be a difference depending on which approach you used here. All right, and then for our normal conclusion, we are 95% confident that the difference in the mean weights of all Target and Walmart bags is between, and then we can use our 2 numbers that we got. Now, depending on which confidence interval you wanted to go with, you could say between 594 and 6,589 grams, Or you could have said between 1,073 and 6,110 grams. Whichever one you do is, again, 100% fine there. So the question I leave you with, do plastic bags from Target and Walmart really differ in how much weight they can hold? I want you to use that calculated confidence interval. And really, you could use either of those two confidence intervals because they should both give us the correct decision to make about whether these two bags really differ in how much weight they can hold. And we'll talk about that the next day in class.